Okay, today we're going to talk about asymptotic notation. So big O notation and other asymptotic notation. So big O of g of n is the set of functions which grow no faster than g of n. G of n is going to be an upper bound on how fast the functions of the set big O g of n costs. Now when we talk about how fast functions grow, we're going to ignore constant multiples. We're also going to ignore small values of n, because we sort of care what does g of n do as n grows large. I'm not so worried about what happens for small n. So formally, we say the set of functions big O of g of n is defined to be the set of functions f of n such that, well, n falls in the function if these conditions hold. Well, what are the conditions? There exists some positive constant and some n naught such that for all n bigger than n naught, f of n is no bigger than the constant times g of n. Wow, it's like poetry, right? All right, so let's look at that again. So first of all, this weird symbol in the middle, I'm reading as such that, but we have, great, f of n is in the set if f of n is less than or equal to a constant times g of n for some constant g of n, for some constant c, and for n sufficiently large. I don't care if f of n is bigger than g of n for small values, as long as for big enough values of n, the constant times g of n dominates f of n everywhere, then f of n is in the set big O of g of n. Usually we talk about this in the context of, oh, we have some function, the function we're interested in talking about, we say it's a member of the set big O g of n if exactly we can find a constant such that for sufficiently large n, f of n is bounded by g of n. Now you notice here I keep on saying everything's bigger than or equal to 0. For our computer science, when we're talking about runtimes, we're not going to have to worry about negative runtimes, right? So we're always going to assume that our runtimes are non-negative. So we're really only going to be dealing with positive or at least non-negative functions, right? So sort of think about what that looks like a little bit more visually. We imagine, you know, you have some function, right? And it grows at some rate, and then you have some other function that, you know, might end up higher, but maybe it started lower, right? Hey, it's negative. Let's try that one again. Maybe it started lower. Now both of these functions keep going, and it's beautiful. It's the thing of beauty, right? We can see this function we expect to be higher, even if the other function was a little bit higher to start with. So let's actually here. Let's make it so that this function ends up higher. The other function started higher. What technology does for us. It's wonderful, right? So great. If we sort of step a little bit beyond this technology and say we got not just technology but wishful thinking, we can do something like, you know, okay, Google, now clean that freaking graph, right? So there we go. We got this great graph, and in this case we say, look, the green graph starts out higher, but once we get past, say, n equals 8, the blue graph is going to be higher, right? So in this case, we want to show 50n squared falls in the set big O of n to the fourth. 50n squared grows no faster than the function n to the fourth, right? Well, that's going to be true if and only if there exists a constant bigger than 0 such that for sufficiently large n, 50n squared is less than or equal to the constant times n to the fourth. And we see here, hey, if we use this as n naught, we could use as n naught 8, and then 50n squared is less than or equal to 1n to the fourth, right? So 50n squared is going to be less than or equal to 1n to the fourth for n at least 8. So great. C equals 1, n is at least 8. For all n at least n naught, I want to show that this holds. Just right back to our basic definition. So does this hold? The claim is 50n squared is less than or equal to cn to the fourth for n at least 8. We can cancel out our n squared terms, and it's true. I mean, 50 is less than n squared if n is at least 8. So great. 50n squared is a member of the set order n to the, n to the fourth. Big O of n to the fourth. Okay? Now, in that example, it sort of didn't matter what constant I picked. I picked 1. 1 was convenient, but n squared grows much slower than n to the fourth, so really no matter what constant you picked, it would have worked out. In this case, I actually picked two functions which have the same order growth. I want to show that 5n squared is in the set order n squared, okay? Now in this case, I can't pick an arbitrary constant, but I can pick a constant, any constant 5 or larger would do, so I pick one. In this case, I'm going to pick 6. We see our f of n function, 5n squared, is for n, every value of n at least 1 and bigger, let's say, is less than or equal to 6 times g of n. 6 is our constant, and 6, n squared, is bigger than or equal to 5n squared. So we know that 5n is in the set big O n squared. 5n squared is in the set big O n squared, right? So generally we use this to simplify functions. So instead of just saying, you know, oh great, 5n squared is in the set n squared, that's nice to simplify 5n squared, but it's even nicer to take, well, the nasty function 5n squared plus 17n log n plus 43n minus 2, that's also in the set n squared. Hey, that looks sort of much nicer to write. You could write it the other way around. You know, the function n squared is in the set big O of 5n squared plus blah, 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 whatever. That's not what we usually use it for. We usually want to simplify what the functions are. This happens to be true, but, you know, just not the most helpful thing to write, okay? You can also write things like, well, n squared is upper bounded by, n squared is in the set big O n fourth, right? It's a function which grows no faster than n to the fourth, but I prefer to have, you know, to have it, this big O function be smaller, right? Big O of n to the fourth is a set which is a superset of big O n squared. So saying that n squared is in the set big O n squared is a stronger saying than saying n squared is in the set big O n to the fourth, because one is a superset of the other. Historically, we don't use this set notation. We use equal notation. People say n equals big O n squared, but really big O n squared does refer to a set, and equality really does refer to set inclusion, all right? We have some other asymptotic growths as well. You can define all of them in terms of big O notation. So we have a f of n is big omega of g of n. That's a lower bound. F of n is big omega of g of n. If f of n is lower bounded by g of n, if and only if g of n is upper bounded by f of n. You also have f of n is theta of g of n. That means it's a tight bound. F of n is both upper bounded and lower bounded by g of n. It's big omega and big O, okay? We also have these sort of strict bounds, or you know, we say f of n is little o of g of n. That means f of n is upper bounded by g of n, but it's not a tight bound, okay? For sure, g of n grows faster than f of n. This is like the example we saw. N squared is little o of n to the fourth. N squared is big O of n to the fourth as well. However, n squared is big O of n squared, but it's not little o of n squared. Little o means it's going to be a 9 tight bound. Also, f of n is little omega of g of n is going to be a strict lower bound, okay? Even though you can define all of these in terms of big O notation, really it's probably more constructive to define each of them more mathematically like we defined big O to begin with, okay? So we had this big O notation. We can give a similar definition for big omega. F of n is big omega of g of n. It's in the set big omega of g of n. It's lower bounded by g of n if there's a positive constant such that for sufficiently large n, f of n is at least as big as c times g of n. Now this is probably a place where this positive c comes in really important. When you're talking about positive functions to begin with, for big O notation, you're probably going to be talking about a positive c anyway. Where are we? You're probably going to be talking about a positive c anyway, but we never want to allow ourselves a negative c here. I don't want to say, look, n squared is bigger than or equal to negative n cubed. That doesn't really, we can't use that to show that n squared is lower bounded by n cubed. You got to have positive constants here, all right? We are going to use sort of both our big O and big omega to have our theta term. When we have little o notation, instead of saying there exists a c, which gives us a bound, any positive c will do. For instance, n squared, 50n squared even, is less than or equal to any positive constant times n to the fourth. Now, depending on what positive constant you're going to give me, I'll have to sort of set a bigger n naught, because it's bigger for sufficiently large n, not for every n. But if you say, 50n squared is, in fact, less than or equal to n to the fourth, that's for c equals 1, if n is at least 8. Or, if c is half, then maybe I say, well, and I want n to be at least, I don't know, 10, let's say, or some bigger number. Similarly, f of n is little omega, has a similar definition. Now, you're going to have to sort of work with these and practice with them on your own a bit. Just watching me practice with them won't help so much, but I just sort of wanted to mention what they are. Also, I can change the order here. The reason we change the order here is to sort of say, look, in some sense, this f of n is kind of like saying, it's like saying f of n is less than this is kind of what this means. It's sort of similar to saying f of n grows strictly slower than g of n. Okay. This one is going to be like less than or equal. This one's going to be like equal. This one's going to be like greater than or equal to. This one's going to be like greater than. So if we stick in some order, we see there's a little bit more structure to what these mean. That sort of tells you why there are 5. It's because we have, sort of 5 inequalities, standard inequalities. All right, so we should also remember these aren't really equal. They are still sets. Every single one of them is still a set. All right. So what's up next? Let's look at these illustrations. I give you 3 functions. And I want to sort of talk about this middle function. My function I'm talking about, the most important function here, is going to be n squared. And I want to talk about n squared in terms of itself and 2 other functions, n cubed over 10 and 10n. We aren't going to care about what happens for low order terms. What we care about is what happens for high order terms. So n squared here is, well, n squared is upper bounded little o of n cubed over 10. It's also big O of n cubed over 10. It also is lower bounded, strictly and non-strictly, by 10n. We can sort of see that. Oh, n squared is little o n cubed over 10. It's also big O of n cubed over 10. It's also sort of a function is, of course, big O theta and big omega of itself. And it is big omega of 10n. It's lower bounded both strictly and non-strictly by this other function, right? We sort of see this gives all the nice relations between this green function and all 3 functions, okay? Does that make sense? Of course, usually within the parentheses, we don't have those constants. And then this looks, great. N squared is little o n cubed. N squared's big O n cubed. N squared is big O n squared, but not little o n squared. N squared is theta n squared. N squared is big omega of n squared, but not little omega n squared. N squared is big omega n. N squared is little omega of n. Anyway, we'll continue this in part 2, and thank you for listening.